Hello everyone, my name is KR Shivardhan. I am from CSMA section. My topic is de Broglie's hypothesis. So in this video we will discuss about the de Broglie's hypothesis, de Broglie's wavelength equation, dual nature of electrons and introduction to the de Broglie's hypothesis and significance. Now we are discussing about introduction to de Broglie's hypothesis. The de Broglie's hypothesis proposes that particles such as electrons have wave-like properties. Means we know that the electrons have the particle nature, but our de Broglie scientist will say that the electrons also have the wave nature. It means it has the dual nature, particle and wave. It is named after physicist Louis de Broglie, who introduced the concept in 1924. The one who invented the de Broglie's hypothesis is the Louis de Broglie. This hypothesis laid the foundation for the field of quantum mechanics. This de Broglie's hypothesis is the main basement and the foundation for the field of quantum mechanics. Now we will discuss about the dual nature of particles. As I told you, dual nature means the both particle and wave nature. According to the de Broglie's hypothesis, particles exhibits the both particle-like and wave-like behavior. Those are known as dual nature. This duality is illustrated by the wave-particle duality of electrons in the famous double-slit experiment. It is experimentally proved by the double-slit experiment. As we know, Young's double-slit experiment, who was invented is Young. The de Broglie wavelength lambda is inversely proportional to the momentum of a particle. Now we will prove this de Broglie's hypothesis by the equation, making equation for the wavelength. It is known as de Broglie's wavelength. At the next slide we will discuss about that. As we will see now, de Broglie equation, wavelength of matter waves, lambda equal to h by mv. This is called de Broglie's equation. Now we will discuss about the de Broglie's equation. Now we will discuss about de Broglie's wavelength equation. The de Broglie wavelength of a particle is given by the equation lambda equal to h by p. Means wavelength is inversely proportional to the momentum and wavelength equals to h by p. H means the Planck's constant, where h is the Planck's constant, p is the momentum of the particle, as I told. This equation shows the relationship between the wavelength and momentum of a particle. The de Broglie wavelength is significant in understanding the behavior of particles on the quantum scale. Here we will discussing about the electron, means particle, which we are noticing that it has the wave nature. Now we will discuss about the electron in this equation. Lambda, wavelength of the electron, equals to Planck's constant by mass of electron into velocity of electron. By solving it, we will get some lambda value. As we will prove that when lambda value equals to 0, then it doesn't has the wavelength, means it doesn't form the wave. But here it will give the lambda value, so it has some wavelength and it will form a wave. Means electron forms like a, means behave like a wave nature, means electron has the dual nature, as it is proved like this. De Broglie proved this experiment with the de Broglie's wavelength equation. Now we will discuss about the wave-particle duality. The de Broglie hypothesis reconciles the wave-particle duality of particles in quantum mechanics. It suggests that matter like light, we know that light is a matter, can exhibit both wave-like and particle-like properties. This duality challenges classical physics and introduces a new way of understanding the behavior of particles. This duality will introduce a new way of understanding the behavior of particles, means particle, how they behave in their surroundings, means wave form in particle form. By this wave particle duality we will understand. Now we will discuss about applications of modern physics. The de Broglie hypothesis has paved the way for the development of quantum mechanics and modern physics. As I told, the de Broglie hypothesis is the main foundation for the quantum mechanics. It is fundamental to our understanding of the behavior of particles at the quantum level. And applications of the de Broglie hypothesis can be seen in fields such as particle physics and quantum computing. significance in quantum mechanics. In quantum mechanics, the de Broglie hypothesis is essential for describing the behavior of particles in wave functions. Wave function means the it is denoted by the psi, means the probability density where the most of the electrons are placed in the atoms. It plays a crucial role in the wave function collapse and the probabilistic nature of quantum systems. The de Broglie wavelength provides insights into the wave-like properties of particles in the quantum mechanics. De Broglie's contribution to physics. Louis de Broglie's hypothesis revolutionized the field of physics by introducing the wave-particle duality of matter. His work earned from the Nobel Prize in Physics in 1929 for his groundbreaking contribution. He got Nobel Prize. De Broglie's idea laid the foundation for the development of quantum theory and changed the way we perceive the nature of particles. De Broglie proposed that matter and slow-moving particles has dual nature. This is the main principle for the de Broglie's hypothesis. De Broglie derived his equation using well-established theories: Planck quantum theorem, Einstein theory of relativity. Now we will discuss about impact on modern science. The de Broglie hypothesis has had a profound impact on modern science, influencing fields such as quantum physics and nanotechnology. Nanotechnology, which will be assisted by our voice. It has led to advancements in technology such as electron microscopy and particle accelerators. Understanding the wave-particle duality of matter has opened up new possibilities for scientific research and innovation. Thank you everyone. Thank you for your attention. We hope this presentation has provided a clear understanding about de Broglie's hypothesis. Thank you.